Hello and welcome to this bare metal programming series where we're building firmware for a cortex-m STM32 microcontroller. Now this is actually episode 3 of this series, and today we're going to be focused on a really important peripheral in the microcontroller, in kind of all microcontrollers in the STMs as well, and that is the concept of the timer. And we're going to be sort of very specifically looking at one use of the timer today, although there are multiple uses, and we'll touch on that a bit. But we're going to be looking at something called PWM, pulse width modulation. And well, if you don't know what that means, don't worry, because by the end of this episode you definitely will, and you will also understand how to configure your microcontroller to be able to do that. The reason I actually want to sort of take this almost divergence into PWM is because, well, it is just such an important concept, and it gets used in so many different places for so many different things. And if you kind of understand that, you get a real grip on kind of these very useful signals that we use both internally in the microcontroller and sort of to interface with the outside world. Alright, so without further ado, let's actually take a look at the plan for today. So the plan for today is first to mention a little bit of important follow-up, and that is that Scott NM on Discord submitted a patch for getting the project up and running with the ST-Link, so being able to do debugging and being able to load the code with the ST-Link. And this is great news, right? Because I'm using a kind of specialist setup here with the J-Link. But if you just buy the board, the Nucleo board that I recommended back in episode 0, well, that will actually have a little ST-Link header on it, and with this patch now, it means that you can actually just follow along with the project completely without touching anything, and you can just use the ST-Link. So that's really nice. If you come over to the drop-down menu for debugging, you'll see that there are two J-Link possibilities here, one for debugging the application, one for attaching to an active application, and you'll see that there are also now two ST-Link options for the same thing as well. So if you just pull the code, that should work for you. If something doesn't work, please open an issue on GitHub, and I'll try and fix it. And yeah, hopefully everyone will be able to use whatever hardware they come into the party with and make little adjustments. And yeah, all right. So the next little thing that I want to do in the beginning is to just prep the project as it is now into a kind of multi-file project. Right now, we've got a single C file called firmware.c, and in that file is kind of everything. And that's fine for now because we have just over 50 lines of code. But eventually that's going to get a little bit much, and you kind of don't want to mix everything together. This is kind of true of any kind of programming. You don't really want to put all your stuff in one place. And we're going to look at just how we can set this up today for multiple files. And by the end, we'll have a couple of different files, and they'll all compile and link together nicely. And if you kind of want to add more files and experiment on your own, you'll kind of have a base to do that as well. And the second part is when we're going to look at PWM and kind of timers in general, and how we can actually use PWM to output a variable duty cycle on the LED to create a fade effect. So basically right now what we have on the firmware is that we're blinking this LED at the moment 10 times per second. But what we can do with PWM is we can actually sort of create a smooth range of brightness on the LED. And we'll see how that actually works and what this means, like this word duty cycle. Like if you've heard of this kind of stuff before, maybe you've used PWM in other contexts, maybe in Arduino or something like that. And I still think this will be useful if you're coming from if you're coming sort of fresh to STM, because the way that the STM peripherals are set up is quite specific, and we'll also get to explore how libopencm3 kind of maps that out too. So let's start with the creating a multi-file project. What I want to do is basically split some of these functions off into their own file. So what I'm actually going to do is I'm going to create a folder inside here. I'm going to call it core. And inside core, I think we're going to put this systic setup and all of the systic related stuff and the RCC setup. And I think we'll just store all of that kind of stuff in one place that's going to be our core, because like those parts, we're not going to touch them too much, and eventually we can sort of share some of that code with the bootloader, and we'll see how we kind of divide the project up more and more to be able to do that. Alright, so I'm going to do the same in the includes folder. So I'm going to create a core, and I think the first thing to do is to create a system.h. You'll see that my editor has chucked these include guards in. That's an extension that I'm using for VS Code. I don't remember what the name is, but it's something like include guards. I don't know, something like that. And you can specify how to name these includes. So that just saves a little bit of time there. And what are we going to put in here? Well, we're going to have this function, right? We're going to expose this function to the outside world. And we're going to have I'm just going to bundle all of the setup into a single function called system setup. So what I think I'll do is to put this in here, and instead of calling it systic, we'll just call it system setup. So right now we're in the header file, and we're just declaring the functions that are going to be part of this system like module, so to speak. So we'll also have get ticks. So that is actually something that returns a uint64t, and we'll call it system_get_ticks. And again, these are void because they don't take any arguments in. You'll see we don't have the this type name by default. This isn't an actual type name in C until you include the right file for it. We have those in a header called common.h. Common.h. That is not the right common.h. No, it's called common defines. So in common defines, we include standard in and standard bool. So we can find those in there. I'm not sure if something has actually changed there. Okay, so now we have the uint64t, and we're exposing this, I guess we can also put these things in there, so the CPU frequency and the systic frequency. Let's actually put these in here, and that means that these will be available also to other parts of the system. So if we need to know the system frequency, we can come and use this same thing by including the system header, and the same for the systic frequency. And you'll see that they're now missing from here. Okay, I think that's it. Now we can go to the C file. So we can create a system.c. System.c. We can straight away include core/system.h. And now we can implement the functions. So these are the public functions that we're going to implement for this module, and we're also going to have some private ones as well. So let's bring in these private functions. So all this kind of stuff we can just cut and paste. So we're going to have this internal. This has to be. We'll find out the warning. I think it's static. I'm not sure if volatile or static is meant to come first. I think static needs to go first. And maybe actually it can't. We'll see. We'll see what the compiler says for this. So this is going to be our ticks. It's sort of an internal to this module. We're going to have our systic handler, which increments ticks. We're going to need to bring in the vector and the systic includes in here as well, and the RCC, although we're going to need to share that, but we'll bring it in from here. I think that one's going to need to stay because we're going to still need some RCC related things here. Okay, so we've got the getTicks that's no longer static, and it's no longer just getTicks, it's system getTicks. RCC setup, that's still going to be the same, and then that's kind of a private function. Then we're going to have our system setup and our system getTicks. Well, we already have that, so, and we can move all of the public functions together. So the system setup is going to be the combination of the systic setup, which we're also going to bring over. So let's bring that up here. We're going to have the systic setup, and before we run that, we're going to want to do the RCC setup. Okay, and this is our C module now. So we've got a lot. This is now a lot lighter, this file. And let's include core system.h. Now we sort of can see those functions here, and we can replace systic setup and RCC setup with system setup. Okay, so this is the code. In order to get this code to run, we need to modify the make file. We need to go and basically say that these other files exist. Now, there are ways to set up a make file so that all of the files are automatically recognized, and that is a fine way of doing it. But for the simplicity of I like to sometimes just list out the files which are going to be compiled. I don't think that's actually a bad thing to do at all. I think it makes your project quite explicit about what's used and what's not used. Yeah, so that's what we're going to do. So basically, inside this make file, there is eventually a little section that says source files with this objects thing, and we're sort of adding objects to it. This first one here is in the source directory, and it's binary.o, and the binary is firmware. So this one is going to be firmware.o. Where are we? So basically, this one is just listing out this C file, the firmware file. So all we're going to do is just add to this. So we're now in the core directory, and it's going to be system.o. So now when we run the compiler, what should happen is it should also compile the system.c file, and then that system.c file becomes an object file, a .o file, and that's basically it contains object code, and later on that can be linked together with other objects to make one application. That's kind of what we do when we make the firmware elf file, and then eventually extract the raw code that goes on the microcontroller. Okay, so let's see if this actually works. So let's run make, and there is now a problem. So the problem is that we're trying to call getTicks. Well, we don't have getTicks anymore. We've got something called system.getTicks, system getTicks. No dots there. Although in my mind, you know, the system underscore is basically kind of like the namespace of the system. So that's that. And well, we're missing something else. We are missing an undefined reference to getTicks. And the other part is, no, that's all just undefined reference to ticks there. So let's run make. It seems to have run successfully. So I'm actually just going to debug the application. And I'm going to take a glance down on the desk. And it's running exactly the same as it was before. So that tells me that we didn't break anything. So this is good. This is a good basis, and for any other kinds of like new files, we're going to do exactly the same thing, right? So if we need to create something new from this, which we're going to do very shortly, we're basically just going to create a new C file. It's probably going to have an associated header file, and then we will just add it into the make file, compile, and it should work automatically. Okay, so the next part is going to be looking at PWM. So what is PWM? Well, for that I've prepared some kind of diagrams here. PWM is essentially just us putting out a kind of signal on a pin or internally. It's basically just a square wave. So if you're familiar with, music, especially video game music, the kind of the sound of a square wave is actually really characteristic. And it's kind of for a lot of people of my age and older, the sound of a square wave is really like the sound of childhood playing video games. But PWM is not necessarily a square wave. It's kind of like more like a rectangle wave in a lot of ways, because kind of what you can do is you can kind of create a wave of a particular frequency, right? This is a fixed frequency that's going out, and you can see that it goes up and down and up and down, and kind of the spacing is kind of fixed in this way. So any point peak to peak, that's what we would call the period. And the period of a wave is intrinsically tied to its frequency, right? The period is just like how much time is it before like the beginning of one like peak of a wave to the next peak. And the frequency of a wave is just like how many of these periods do we have per second, or whatever measure we're using. If we're using hertz, we're measuring sort of these periods per second, these cycles per second. So this is kind of the period. And then we have something called the duty cycle. So this is really specific to kind of PWM and square waves. So the idea of the duty cycle is like, well, how long is the wave kind of in the positive state, let's say? How long is it like high for, logic high? And how long is it low for? So the amount of time that the wave is high for, that's kind of the duty cycle. So in this case, we have a wave and it's 50% of the time it's high, and 50% of the time it's low, right? It almost doesn't matter about its frequency at this time, right? This could be going like, this could be like 1 second between this point and this point, in which case we would see it with our eyes blinking, on, off. But it's on for 50% of the time. So if you imagine like speeding this up to a point where your eyes couldn't distinguish it anymore, something like, I don't know at what point your eyes would stop distinguishing it, but let's say it's already 500 hertz, 500 changes per second, 500 cycles per second rather. So if we had a frequency of 500 hertz and we had a 50% duty cycle, and then we changed the frequency to 600 hertz, and then we used that to light up an LED, well, what we would see is exactly the same between those two frequencies. Like, that wouldn't appear different to us because the light is always just on for 50% of the time. Like, overall, continuously, 50% of the time. So that's kind of what the duty cycle is kind of getting at. And you can see here we've got a wave with a larger duty cycle. So this is more like a 75% kind of duty cycle. So 75% of the time it's on, and then sort of 25%, maybe that's a bit less, maybe this is more like 80%. But yeah, it's off for that last little part. So it has a higher duty cycle. And you can imagine, you can scale this wave all the way back, and you can have a very small amount of time that you're on for. And if the wave is just permanently off, then that's a 0% duty cycle. But notice between these two things, the period is exactly the same. So like, there's no frequency relationship here, right? We can have a larger duty cycle or a smaller one, but the same frequency. Okay, so let's imagine for a second that you had to design a system, either by writing some code or by making discrete electronic components, putting discrete logic gates and transistors and things like that together. How would you build something that could, given a sort of a clock input of a given frequency, could output a wave that allowed you to do a variable duty cycle? How would you do something like that? And how would you also then maybe allow that that wave to change its frequency. So to be able to do it at different frequencies, but still also be able to change the duty cycle. Now, it's not necessarily obvious. You don't have to come up with the answer right now. So I will show you. So this is basically a simplified model of how it actually works. And there are basically three register values, three kind of things we need to keep track of in order for this to work. So the first is like a counter. So what you can see here on the graph here is time going off on this direction. And this kind of little staircase you see is just a counter that's going up. So, you can imagine it's 0 here, it's 1, 2, 3, and it's just counting up to a certain point. And once we get to a certain point, we reset and we start counting again. So we drop back down to 0 and we start counting again. And again, if you're familiar with music, this is another familiar wave. This is a sawtooth wave. Also very characteristic in video game music. So the idea here is that, like, let's say our clock that's driving this whole circuit, or if you're imagining purely from a code perspective, this would just be the fixed frequency by which we call the function, which is incrementing this counter. The clock that drives this, it drives at a fixed rate, and we increment. So this is just a register, a counter that's going up, and the value that we count up to, well, we can store that in another register. And on the STM chips, that's called the auto reload register, the auto reload value. And that's basically what it's saying is like, oh, okay, once you get to this auto reload value, drop back down, start counting up again. And I'm saying counting up, you can do exactly the same thing by counting down, right? You would imagine that you would, you would start at a particular auto reload value and you would count down each time. And when you hit 0, you load the auto reload back up and then you start again. It actually doesn't matter. You can do up and down. And on the STM chips, you can actually configure whether you're going up or down. There are different, it doesn't matter so much for now, but in different situations, you can make use of that. Okay, so then we've got this value. So you can imagine we've got a fixed frequency that's driving this circuit, but the value that we stick into the auto reload is actually going to define its frequency, because if we have our auto reload here, for instance, well, we're going to have like twice as many peak-to-peak waves, which means that we've doubled the frequency. So actually by changing this value, we can modify the frequency of like how often this thing is ticking over. Okay, and then we have another register called the compare value, the capture and compare value, or capture and compare register. And what we do in here is we set a point to compare the current counter against. So we load this with some particular value, like I'm not sure what this is, but it's like 50% of the way up of this on this wave. So we would load in that value, and then what we're doing is we're saying that there's another circuit, a comparator, that is able to look at the difference between our value of that we're counting up and this compare value, and basically we're going to say, well, it's a 0 if the counter value is less than the compare value, and it's a 1 if the compare value is greater or equal to the counter value. And what you'll see is that actually allows us to generate a wave like this. So you can see, like, at this point we're just counting up, so we're all low here because the counter value is less than the compare value. And then eventually we get to this point where they cross over and the compare value becomes equal to or greater than the counter. And at that point the wave snaps up and our output is high. And then of course we get to the auto reload, we drop back down, that puts us at 0, the counter, and then we're back down again. So this is the essential, like the core of how PWM works. We have a couple of register values, and just by comparing them and using the output of that comparison to be our sort of our final output, that's how we can generate this PWM. And of course you can imagine, right, that we move this compare value down here. Well, now all of a sudden the wave's going high here, and it's staying high for a long time, then it's dropping back down. And then again it's low, and so that kind of allows us to control the duty cycle. So we can put that back up around this point, I think. And of course the reload, we can do the same thing. We can bring that down, and all of a sudden now we're snapping back down at this point, and so we've changed our frequency. So yeah, I hope that's clear. It's very conceptual right now, but that is essentially how PWM works. And what can you do with PWM? Well, of course, we've talked about the idea of controlling brightness of an LED. That's what we're going to do today. We're going to use PWM to control the brightness of this LED. But actually, a lot of other electronic components out there use PWM as a sort of interface. It's actually really interesting. Like often you will drive, talk to motor driving circuits with PWM. So there will be a fixed frequency that you have to have, and there'll be some range of duty cycles. And if you drive a certain duty cycle, that will have a certain speed on the motor. And I've seen it that, you can drive a certain frequency and then the motor's turning in one direction, and you drive a different frequency and it's driving in the other direction. So it actually becomes like this interfacing component, because you can build a circuit that's able to recognize PWM on the other side and can extract that frequency information, can extract that duty cycle information, and can use that to make other choices. So you'll often see it driven in kind of interfaces to things like motor drivers. What you'll also see is that it can just be used to drive the output of a MOSFET. So a MOSFET is basically an electronic switch, and by sending PWM to a MOSFET, you can actually switch on an external circuit, which may be running at a much higher voltage or a much higher load. You can switch that circuit much faster. And that becomes very, very interesting when you get deep in the weeds and you start having multiple MOSFETs, and those MOSFETs are really controlling different parts of the circuit. And by driving things at PWM and also having multiple PWM signals that are kind of inverted from each other or are kind of complementary, then you can start doing interesting things where on one cycle you're driving one part of the circuit, and on the next cycle you're driving the other part of the circuit, and you keep them literally in sync but running at different times doing that. So that's very interesting, and that goes quite deep. There are more advanced features to PWM. You can do things like dead time, where you essentially ensure that at the end of any given PWM period, there is a sort of amount of time that nothing is happening on the output for, and that is to allow things like switch time and settling on external switches to settle down, so that you don't accidentally drive two things at the same time that you meant to be completely exclusive. Yeah, so it's quite a useful technique. And of course you can use PWM to make music, right? So that's one of the other really nice uses that you can apply is, well, you can literally make a square wave, and if you put a little amplifier on the output and you plug that into a speaker, well, all of a sudden you've got a tone generator. And just by changing the frequency, you can modify the note that you're playing, and by changing the duty cycle, you can modify the kind of character of the sound. And if you go a little bit further and you put some analog electronics on the other end, so just a little bit, maybe just one resistor, one capacitor, you can build a filter, and you can actually turn your square wave into a sine wave. So if you calculate the right values, so then you can even sort of create different musical tones sort of while the main sound generation is taking place all in the same way. You have a little bit of circuitry on the outside which is able to change the tone of your music quite a lot. So yeah, there are a lot of different uses, and I'm sure that I'm not even scratching the surface here. So where do we actually get information about this? The answer to that is basically always in the reference manual. So here is the reference manual. I spoke about the reference manual in the previous episode. And down here in section 13, and this will be different according to different chips, but you'll always find it in the contents here. You'll find that there is a general purpose timers. Whereas actually in the section above, there is an advanced timer on this chip, so this one is able to do more interesting things. And that's kind of getting towards the more advanced use cases that I talked about at the end there. But we also have this bunch of general purpose timers. And I think it's quite useful just to read through the first couple of sentences here. So the general purpose timers consist of a 16-bit or a 32-bit auto reload counter driven by a programmable prescaler. So the prescaler part, we'll get into that in a minute, but that basically allows us to describe how our overall system frequency, our kind of 84 megahertz that our chip is running out here, how we actually get down to a certain fixed frequency that we drive the timer circuit with. That's before we can change the frequency with the auto reload value. But yeah, this is kind of our programmable prescaler. And the 16-bit or 32-bit auto reload counter, well, that's basically just saying like how much fidelity do we have in actually putting this auto reload like together, like how high can we count? Because if you have a 16-bit timer where you can only count up to 65,000 or so in order to get up there. So if you actually need a sort of wider range than that, then a 32-bit is required. They may be used for a variety of purposes, including measuring the pulse lengths of input signals, so that's doing input capture, or generating output waveforms, output compare, and PWM. So the interesting thing about the timers here is that I've mainly been talking about PWM, but the timers can do a lot of different things. The timers can, like it says, it can allow you to accurately measure input, and it can also, instead of just being used for PWM, we can do things like a single pulse. So we can use the timer and its accuracy in timing to create a single pulse of a particular length. So not a fixed frequency signal that's going on until we tell it to stop, like one single output. And that can be really useful too in some cases. The really interesting thing about the timers in general is that, of course, we can use them to drive output on a pin, but we can also use the timers to drive other peripherals on the chip. So we can use the timers to generate interrupts, which give us really accurate timing. So we have the sys-tick right now. That gives us our millisecond level timing. But if we need to keep like more accurate timing than a millisecond, or we need to set an event and come back to it at a really specific moment, that we can also use timers for. So we're going to focus on the PWM part for today. So let's have a look at the PWM mode. So pulse width modulation mode allows generating a signal with a frequency determined by the value of the TIM X. So this X here is just saying that we have multiple timer registers, and this can be any of them. Auto reload register. The ARR is the auto reload register, and a duty cycle determined by the value of the timer X CCRX register. So that's the capture and compare register. And the other interesting thing, well, there's many interesting things about this, but any given timer is going to have multiple channels. So we can actually set our timer up at a particular frequency, but we can actually compare multiple values and have multiple PWM outputs. And that's a really useful thing as well, because now all of a sudden you have a bunch of signals which are intrinsically synchronized to each other, but can like produce different information. So either complementary, so one is going up, one's going down, or just like one is a 25% duty cycle and one is a 50%. A lot of interesting things you can do that way. So basically this document describes how we can actually set all the different registers up and what they do, and there's actually much more to this. You can set this up in all different kinds of ways. You can set the registers up so that they generate an event when the auto reload hits, and then if you do that, then you can basically change the way that the auto reloaded value comes back in the next time around. All of this kind of stuff is a little bit a little bit like further than we need to go for now. We also have the concept of edge alignment. So basically, like where does the PWM wave happen in relation to the clock? We can do down counting. So instead of that nice steps going up, we could count down instead. And that's interesting if you want to like just change the way that you generate the PWM, right? You always compare the counter to the capture and compare register, but this is like you're always going to do the same kind of comparison, but if you're counting down, you're kind of starting at a different place, so you're doing a different kind of comparison in the end there. All right, there's a lot more information here, and this is basically where you go to figure out all of these different things. So you can see we're actually going through different modes now. So we've also got one pulse mode. So PWM is pulse width modulation. That's like a signal going out, and we modulate the pulse width of a fixed frequency signal. And one pulse mode is, like I said, we output a single pulse at a very particular time. And down here in the last part of the section, you'll get to all of the registers, and this is kind of where you can figure out how you actually set everything up. So you have the control register CR1. And in here we write values like the clock division. So this tells us how to divide the clock down, like the main clock. So there are actually multiple ways in which the clock can be divided down before it actually gets to us. So this is one of them. We have the auto reload preload enable. This is not really important for us now, some of this stuff. The center align mode selection, so basically we can talk about where the wave is aligned to or how different alignments take place. We have the direction, so like PWM and the counter, that's not specific to the timer as a whole. We're actually configuring the timer as a whole with this register, so we could be going in any mode, but the direction which we count is actually just part of the timer itself. And then of course we have the whole one pulse mode thing. There are multiple different things going on here. There's also a second control register, so that has a couple of other different things going on. There are some much more detailed things you can do with setting it up in a so-called master-slave configuration and setting up DMA, so using the timer to drive the direct memory access peripheral, which we might talk about at some point. But eventually the main things we're going to be looking at are the ARR, the auto reload register. This is kind of one of the most important ones. And the capture and compare register, which is this one here. Yeah, so these are the kind of the most important core registers. All right, that's enough looking at the reference manual. Let's actually start writing some code and get this up and running. The actual code we need to write is not a huge amount. Okay, so I'm actually going to create a new file, and do we put it in core? Let's put it in core for now. Just maybe we'll move things around. I'm going to call this one timer.h. And what are we going to have in timer.h? Well, we'll probably have a timer setup. And do we need to have anything else in here? We might want to have some like nice helper functions for PWM. So let's have a function that is a void function, and we'll call it timer PWM set duty cycle. And to this function, we'll take in a floating point value, which will be the duty cycle. So that will be a value between 0 and 100, representing a percentage. And that means that we can actually, when we configure the PWM to a particular frequency, we can actually just specify a duty cycle value, and it will automatically take that. So let's set up these functions for now. And let's make another C file here, timer.c. We will include core timer.h. And let's bring in those two function signatures. So, setting up the timer, we're going to need to bring in libopencm3 STM32 timer. So this is to do with those registers we just looked at, like if we actually open this up and go into this one and follow it through, we'll see that there are a bunch of definitions for various kinds of values. We have some memory mapped I/O registers. We have some different kind of values here. We have some more values here. We have some enums, and eventually we have a couple of functions. There are actually a lot more functions. There are timer, common, all. If we go in here, you'll see all of the different registers, and at the bottom we'll see all the different functions that we have, which is quite a lot. There are quite a lot of different functions that we can use for this, but we're only going to use a handful of them for now. Okay, so timer setup. The first thing to do, this is just kind of common. Is this? Yeah. The first thing that we always need to do is we need to enable the clock to this peripheral. So we're going to do that with RCC perif clock enable, and the peripheral clock is going to be RCC underscore tim2. So we're going to be working with timer 2. And a really good question you might be asking is, why timer 2? Why not timer 3 or 4 or any of the others? Well, for that we need to look in the datasheet. And in the datasheet, down here in the pinouts and pin description, you'll find a big table called alternate function mapping. And basically, the STM32 is quite flexible with what pins can do which functions. So previously we've configured the, what is it, PA5, I think? Yeah, previously we configured PA5, port A, pin 5. We configured it as an output, and we're driving the output. That's the pin that the LED is on. So we're driving that directly by doing GPIO toggle. But we're actually going to want to drive that pin using the timer peripheral. So we need to come down to this alternate function mapping. And if we come here to PA5, we can see that PA5 can be controlled by a couple of different peripherals. You can't do everything. Not all peripherals are able to go to all pins, but in this case, we're able to drive PA5 with timer 2 channel 1 and timer 2 ETR. So we're going to be using channel 1 of timer 2 to drive the PWM output. So that's why we're using timer 2. Alright, so let's zip back to the code. So we've enabled the clock to timer 2. Now from here, we need to do a little bit of setup. There is quite a bit of setup going on here, but I'm going to explain all of the things that we need to do, and I hope you'll understand why there's so much setup involved by the end of it. Although if you're coming from Arduino, this is going to seem like really a lot to just do some PWM on a pin. Okay, so we're going to want to set up the timers mode initially. So this has kind of a couple of different things we need to provide. The first one is just which timer peripheral are we talking about. So it's timer 2. Then we're going to have the clock divider, and this is a uint32 value, but it actually has a specific configuration here. So this is timer 2 CLK. So this is something that's going to be written into the CR1 register, the control register that we looked at earlier. And so I'm just going to select this one and go to the definition. So these are the clock divisions that can be passed to this function. So it can be this one, just int, and you can have, I'm not sure what int stands for actually, int multiplied by 2, multiplied by 4. So you can kind of cut down by half or by 4, in this, and this one just doesn't cut down at all. So we're just going to pass this one as our option. So basically don't do any like division on the total top level of the timer. Next is the alignment. So the alignment, I'm trying to remember exactly where the alignment comes in here. Here we go. So this is the center aligned mode selection. And the options here are edge aligned, center 1, 2, and 3. So we're just going to do edge aligned for now. And finally, this is the direction. So I think there is also a direction here. So we have direction up and direction down. Well, we'll just count up for now. So what we've done here is basically set up the mode of this thing. We've set it up with its divider, with the kind of edge alignment that we have, or the center alignment, and the direction by which we count. So this is just all stuff that's gone to the control register 1. And we can verify that by coming in here and seeing that everything here is just writing to the control register 1. Okay, so that's the first part. And actually we don't necessarily have to do this because this essentially would be the default value, but it's always good to really explicitly set all of these peripherals up as much as possible. Okay, so that's kind of the high level setup here. The next thing we're going to need to do is to set up the PWM itself. So we do this with setting up the output compare mode. So everything is all about output compare in the timer, right? We have this register and we have a counter, and it's all about comparing kind of like the compare register with the counter. So the mode that we're actually going to be setting up here is, well, we're going to be working on timer 2, and here we have an enum, tim OCD. The enum is timer OCID. So let's just search that. Let's go to this function. No definition found. And then go to this one. So here, yeah, we have the different output compare channel designators. So we have output compare channel 1. We have output compare channel 1 negative. So this is just an inverted version of the compare channel. Channel 2, channel 3, channel 4. And as we saw in the table, we're going to be using channel 1. So we're going to take timer OC1, which is the output compare channel 1. Okay, and then we have the OC mode. So again, let's go back here and let's go to where the OC mode is. And here are the different things we can choose for the output compare mode. So we have frozen, active, inactive, toggle, force low, force high, PWM1, and PWM2. So we're going to do PWM1. Not entirely sure what the difference between PWM1 and PWM2 is, but that is what we're going to be doing. And finally, we have... oh wait, have I overwritten here? Wait, so timer peripheral, enum, yeah. So those are our 3 arguments. So we've set up kind of, so this is just like high level, this is the high level timer configuration. This is set up PWM mode. And what are we going to do next? Well, next we are going to, and I do have some notes here, so I hope you excuse me. I didn't want to miss a step here, because essentially if you miss any of these steps, it just won't work. And then you kind of have to do the debugging. I'd rather not do the debugging right now. So the next thing we're going to do is to enable the counter. So this is kind of like the peripheral is running, but it won't count up. The counter won't, the little staircase won't move up unless you tell it to. So we're going to enable the counter. Again, that's timer 2. So that's a simple one. That is a comment that doesn't really need to be run, but let's keep it consistent. Okay, so after that, we are going to set up our output compare. So that's going to be timer output compare, sorry, enable output compare output. Yeah, so what this is actually going to allow us to do is to, we have our our capture and compare register. That's kind of where we put the value that's going to define our PWM kind of duty cycle. But output compare has multiple channels. So the channel that we're going to be outputting to on timer 2 is actually going to be timer underscore output compare channel 1. So that's what we looked at earlier. So we set up this channel, this output compare channel, and now we're going to be enabling that one's output as well. So maybe we can just call this one enable PWM output. So we'll kind of put these things together here. Okay, and the next things we're going to do is actually to set this up for the frequency. So we haven't done any clock division right now. So that means that we have a frequency of 84 megahertz, right? So 84,000,000. That's what's coming into this this peripheral right now. So we need to divide that down. That's too high for our purposes. So what frequency do we want to run at, actually? Like, and actually the question is not just like what frequency do we want to run at? It's also like, as we're running at a particular frequency, how many individual steps do we have inside that frequency? Because you can imagine that if the main clock, let's go back to the diagram for a second here. Here we are. You can imagine that the main clock, right, which defines each of these, if we drive that faster, then of course this pattern, no matter like what auto reload value we put in here, like that's going to be a higher frequency. If we drive it slower, it's going to be a slower frequency. But what the auto reload value does for us, actually, if you think about it, is it gives us this many discrete steps of possibilities, and those discrete steps are going to basically define like kind of how granular we can be in defining the duty cycle of this this PWM output. You can imagine that if we had 100 steps, so if we set the auto reload value to 100, that means we're counting from 0 to 100, and that means we have 100 individual possibilities of where this, like how wide this could be. If we made it 200, but we kept the same frequency driving it in, well, now all of a sudden we have the same wave, but we can actually have like twice as many individual points along the PWM. Now, how many points do you need? That is a question that you can't answer without having some kind of requirements and specifications. I'm going to arbitrarily say that I want to have a frequency of 1 kilohertz, so 1000 hertz, 1000 cycles per second, and I want to have 1000 divisions within that, right? So 1000 individual points that we could place, that we could have for our duty cycle. So how do we actually set that up? Well, the first thing is that we can just do a general clock divider. And the general clock divider, I shouldn't have closed this thing down. The general clock divider is going to get us to the point of, well, like how fast do we drive this? Like how fast are we driving this whole operation? And then when we set the auto reload value, that's also going to define our frequency. Like obviously what we place in as the clock, we can't be faster than that, of course, right? We can only divide down more. Like every time you take a step, you're kind of dividing that clock down a little bit. So what we're going to have is the signal the combined effect of the signal that we divide in and the amount of auto reload is going to be that we have 1000 cycles per second and 1000 divisions within that. So we need to call this function set prescaler, and this is going to be the prescaler for timer 2. And what's the prescaler value? So let's define these up here. The calculation for this, and I didn't want to like put this out there until all of the rest of this was clear, because what's really important is that you understand this conception of how it works. Like, this is the important part, but there is a calculation for how to figure out the frequency that you're going to get for this. So basically, your frequency is the prescaler value plus the auto reload register value. Sorry, it's your system frequency, so the input frequency divided by the prescaler plus the ARR, the auto reload register. So kind of the combination of these two together gives you your overall division. And I hope that makes some sense now, because you understand that the rate in which this moves and the auto reload, where we place this auto reload register, that's a combination of those two things. So that's how we get to a one complete. And just because of a quirk of how this works, because you always divide by something that's not 0, you actually have to account for the fact that the prescaler that we place into this is like 1 minus the value minus 1 of the value we actually want, right? So if we want 8,000, well, we plug in 7,999. And if you've seen some of my videos about compression formats for the for ROM patches, you'll know that sometimes this kind of thing goes into those kind of formats. When, like, especially when you know you can't have a 0 value, like, why would you waste that value that you have? Just have them pass in the value that's kind of pass in 0, that gives you 1, right? You haven't wasted 0. So that's how this works. Okay, so what we're actually going to do is we're gonna first define a prescaler, and the prescaler is going to be well, let's think about this. We want to have 1000 cycles per second in the end, so we kind of need to divide by 84,000 overall. So our prescaler is going to be 84, and then our I'm going to call this the ARR value. That is going to be 1000, right? Because we want to have 1000 steps. So this should be a multiplication. So in the end, if we take 84 times 1000, well, we're then dividing this whole thing down by 84,000. And that gives us 1000 overall, right? And that is what we're looking for. That's the frequency, 1000 hertz. And now we have 1000 steps within that. So that is how this works. I'm going to leave this frequency here so you can see how we get to it. But of course, like, this is going to depend on what clock frequency you're running at and what you kind of want overall. So just keep that in mind. Okay, so now we can actually just pass in the prescaler value for that. And the next thing we're going to do is to set the period. And that's actually the auto reload register. So if we set the period and we go into this function, you can see that in the end we're actually writing to the auto reload register here. So, and both of these values, of course, should be -1. In fact, you know what? I'm going to do that at I'm going to do that here instead. And when we set the period for timer 2, that's going to be the ARR value, -1. Of course, if we didn't do the -1, like, we wouldn't be so far off, but we would be off from what we were looking for. So this is basically set up frequency and resolution. Okay, and then that's actually it. So that's how we've have set up the PWM on the timer peripheral. So it's quite a bit of work that has to go into it. You have to kind of really get the timer figured out, and then set the mode up, and then really set all the values for comparing. and the preload. But eventually, when you do all of that, you're in the right place. So now we actually have this. We can actually implement the duty cycle calculation. So let's think about this, right? If we wanted a 50% duty cycle, a 50% duty cycle would be the value 500, because if we're counting up to 1,000 and we want half, well, we would go for the value in the middle. That's 500. But how can we do that in a generic way so that it doesn't matter what values you put up here? So we're going to take in a duty cycle that's going to be a percentage. So if we take our... let's think about this, right? The duty cycle is actually, if you kind of think about what you want to calculate the duty cycle to be, because there's no intrinsic thing in terms of the peripheral registers as the duty cycle. If you think about how we calculate the duty cycle, that's going to be what we define as the capture and compare register, like the value that we put in to this point, the compare value. It's going to be that divided by our ARR value, like our kind of total value. So like what value are we setting this to, divided by, the total possible value times 100. That would give us a percentage duty cycle. So, of course, you can do some rearranging of this. Like, this is just an algebraic expression now. So we actually have the duty cycle, and what we want is the CCR value. So how would we get that? We can just do some rearranging, right? And then in the end, CCR, if we were to divide both sides by, well, let's just go through the steps here. So I'm sorry if this is insulting to you, but I also want to make sure that I don't mess it up. So the CCR, or sorry, the duty cycle divided by 100 is now equal to CCR divided by ARR. And if we want to isolate CCR, we can just multiply both sides by ARR. So ARR times duty cycle divided by 100 equals CCR, or rather CCR equals ARR. This is a weird formatting. Okay, so this is basically how we're going to calculate that. To get back to this CCR value, the value that we need to set in the register, we're going to take our known ARR value and multiply it by our duty cycle divided by 100. Okay, so const float, let's call this the raw value. This is going to be the ARR value, so we're going to treat that like a floating point value, and we're going to multiply that by duty cycle divided by 100 float. Okay, so that gives us the raw value, and then when we want to set that as kind of the we want to set that as our capture and compare register value. Well, that's going to be timer set. What do you call that? Now I actually am going to have to delve into the code and see if I can find the capture and compare register. Set OC value. Okay. Set OC value. So this is going to be for Tim2, and this is going to be for this channel. So the output compare channel 1, and the value is going to be a uint32 cast of this raw value. So we're going to knock off any decimal places that we have, and we're going to assume that we've been given a sensible duty cycle value. Yeah, so we're making some assumption here, like this could blow up if this was something that couldn't be represented within the raw value. But I think that, well, we would see what would happen in that case. I don't think it would be too bad for this situation. But yeah, you would want to put a proper check in for that if you had the risk that you would receive value that didn't make sense. Okay, so this is kind of all of the actual timer code that we need for this. Now we actually need to set up the LED itself, because right now we've got this GPIO set up, and the way we're setting up the GPIO here is not going to work. We can't drive the pin just directly like this, so we're going to need to change how we do this. So going back to this document, we can see that if we want to have PA5 driven by timer 2 channel 1, we need to use alternate function 0,1. Like alternate function 0,1 basically in this context means PWM output or channel 1 output compare. So it doesn't have to be PWM, it could be pulse mode, but that's what it is in this case. So we're going to use the alternate function mode instead, and we're not going to have any pull up or pull down. We're still talking to the LED pin. We actually need to do a little bit more configuration here. So we need to set the alternate function of this pin. So again, it's still just the LED port. And in this case, the alternate function is GPIO alternate function 1. And the GPIOs, because we could do multiple, but it's just the LED pin. So now we've actually set up the LED to do PWM output on this pin. So we have system setup, GPIO setup. Let's do our timer setup. For that, we need to bring in new header there called timer setup, and we're still gonna be making use of our system time here. But what we're gonna do is we're gonna have a variable here called duty cycle. We will start it at 0, and let's initially set our duty cycle to be that. So it's got a well-defined value going in. And so right now we're doing something every 100 milliseconds. Let's do something every 10 milliseconds for now. And instead of toggling the GPIO, well, now we're going to, let's do something like this. Duty cycle plus equals 1. And if the duty cycle then exceeds 100, we will set it back to 0, and then we can just call this function. And then we're going to be waiting for, basically waiting until we've gone 10 milliseconds. So I'm going to try and run this. I'm probably going to have made a mistake, so let's actually first just run make. Now, of course, yeah, we need to list that we're going to build this file. So we're going to have a bunch of things missing there that seem to have built. So I'm going to run the debugger. Press play. All right, and now I'm going to change the camera view, and I hope you're going to be able to see this. So I'm not sure how well the camera is going to pick that up. I hope it will focus. It's not focusing. That is unfortunate. But what you'll see there is that the LED is changing in brightness. And it's basically taking about 100 milliseconds to go from... Sorry, no, that's not quite true. It takes 1 second to go from complete darkness to full brightness. Now, the thing about brightness and LEDs and human perception is that you actually can't see linear progression of brightness, especially on different colors. So if it's going to make a difference whether the light is green or red or blue, but in general, our eyes cannot see linear changes in color. So that change in color, I mean, at least to me right now, and probably on the camera as well, it doesn't look like it goes, uniformly. It seems to ramp up with a kind of exponential curve. That is normal, so don't worry about that. That is totally true. And if we were to put the output of this LED, if we were to look at this on an oscilloscope, Maybe we'll do that on the next in the next video. If we were to look at that, we would see this nice, clean, like fixed frequency, but changing the duty cycle constantly wave. And we could totally mess around with the frequency and things like that, and maybe we can hook this up to a speaker. But the main idea here was really to give an overview of quite an important concept of timing and how we can use the timer peripherals to do even more work for us, right? We don't want to write the code to generate that wave. We want to have the peripheral do the hard work of generating that wave for us. You can see we don't have to do any work in here in order for that to happen. All we need to do is add to a floating point value and make sure it doesn't overflow. Call our duty cycle function, and we get a variable output on that pin. Great. So I hope this has made some sense to you. I hope if this was a concept that wasn't clear before, that you've gained a little bit more clarity. And as we go forward in this series, I'm going to try to just, explain out the important subjects. If there are things that you also want to see covered, of course, we're going to end up going towards writing the bootloader with a signed firmware update mechanism. But along the way, I think it's also useful to look at different peripherals and just explore them. Not all of this is just a race to the finish line. I really want to also underscore the importance and the main concepts that go into these kind of things. So let me know if there are any interesting concepts that you want to cover, any peripherals that you would like to take a look at. But for now, I'll see you in the next